Okay. Okay, we are now recording. Let me get the setup from the current slide. Okay. I think this is the slide we left off of last time. Announcements. Okay. So some of you are obviously in a second mini-term course. If any of you are on Pell Grant, then the Pell disbursement should have been today. Now, if you have direct deposit, it should be in your bank account already. If not, you need to go by the, I guess, cashier's window, business office window, or whatever to pick up your check. Okay. That's all I see that would be of importance there. Now, the volleyball team, today's the, whatever the day is. I don't have the dates on here. 22nd and 24th. Okay. All right. Today, this evening at 6 o'clock, unless y'all are in a really big hurry, you probably are going to have trouble making it. Our volleyball team is hosting LaGrange College JV, and it's called Sophomore Night, whatever that means. That's 6 o'clock, Birmingham West Campus, on the, and there's Diamond. All right. Just missing Mendez and Latricia. Okay. Then the next matches are not until November 1st, and that's when the district tournament begins in Boaz, Alabama. Now, I can't remember if I announced this or not. I don't know if you're interested. It sounds really good. This is from a Dr. Christina Mora, who's at UAB. She says she's one of the newest cohort of merit scholars at UAB, and I have no idea what that means. But she came across this 1-week summer opportunity for college students interested in biopharma, that's biological end of pharmacology, meaning drug making, manufacturing careers, and thought one of your students might be interested in applying. The students are paid, get this, for a 1-week summer opportunity, this coming summer, paid $1,000. And travel expenses are covered. How can you beat that? Now, even if you're taking classes this summer, you can probably talk to your instructors and manage to get out for 1 week. But boy, what a deal. The application deadline that says is sometime in January. That's not very specific, but it's a while off. I have a link here that you can go for a website to get all the information you could possibly need. So if anyone's interested, it's up here. You're welcome to copy it. Okay. Now, before we get going today, let's talk about what's happening today. We are going to continue in Chapter 2, and I think there's a fairly good chance that we'll either finish or come awfully close to finishing Chapter 2 today. Okay? We have a lab this evening from 5:45 to 7:45. I don't think will take you that long to do. It's sort of a fun lab. It will be across the hall from where we've been being. It's in 252, not 253. There's a reason for that. We needed a longer lab table, and they don't have those little hexagonal ones in the other lab. They're just too short. So we're set up on the other one. So we will be there for the lab today. And since we don't have a test, the lab will be 5:45 to 7:45, but I'm almost guarantee you most of you will be through before then. Oh, one other thing before I should have done this before I started recording. The last person turned in the first lab, and this has to be a new indoor record for me for this class about students getting their labs in on time, okay? Fantastic. Way to go, folks. Okay? Keep it coming, okay? We had a few people absent last lab, and at least one's come by to pick up lab sheets. So Patricia's not here. Frank is. Jose or Mendez is not. Mark is. Pages came up. Diamond is. And Ryan is. All right, way to go. Okay, so we will be the last 2 hours of the day, the regular lab time, we will be in lab, or at least until you finish the lab. All right, any questions on anything we've covered so far? First chapter, first test, first lab that you just got back, or what we've done so far in chapter 2?
Are we going to go over the tests? Can we go over the tests?
Not yet, because not everybody's turned them in.
The test?
The test, yeah. There were 2 or 3 people absent last time. They haven't taken the test. Yeah. So I don't want to answer questions on the test now. They can hear them, and that would not be good for you, okay, for your score. Okay. You can see your scores. They should be out there on Blackboard, but if they're not, I can certainly show you your test, and I'll answer any questions. So if you'll see me, probably after lab would be the best time, because we'll be through in plenty of time, I think, or at break or whatever, okay? But yeah, you can see your test, and I'll answer it individually, but I can't do it before the whole class because there's people who haven't taken the test. All right. Any other questions? Okay. Where we left off last time, we were in the middle of Newton's second law, which deals with, here is the, when you think Newton's second law, think this equation right here. Force is equal to mass times acceleration. Because that's what Newton's second law says. If there is a net force acting on an object of certain mass, then it's going to produce an acceleration. Or, the other way to look at it is, if you have an acceleration of a mass, it's got to have some net force acting on it. Okay? And the net force is the vector sum of all the forces acting on that object. Okay. Now, so after we finished talking about Newton's second law, then they interjected this. This is not necessarily Newton's second law. This is one of the forces that could be acting on any object, and that's the force due to weight. Okay? And so let's back up a little bit. I think we talked about this already, but let's hit it again. Mass is a quantitative measure of inertia. Mass, quantitative measure of inertia. Okay? Other words, it's the amount of matter that you have. Okay? Usually measured in grams if it's small amounts, kilograms, SI unit. Weight, though, is the force that your gravitational field is producing on that mass, acting on the mass. So weight is a force. Mass is an intrinsic quantity of matter. It's an invariant. It doesn't change. Weight can change. If you go out of the gravitational field of the Earth, you're losing weight. You're not losing mass, but you're losing weight. Okay? Go to the moon, you're about 1/6 the weight, still have the same mass. Mass is an invariant. Weight varies with the gravitational field in which you're located. And we spend most of our lives, probably all our lives, in the Earth's gravitational field. So our weight doesn't vary because of that. Maybe other things, but not because of that. So pounds for U.S. customary, newtons for SI, those are units of force or weight. Okay? Kilogram, SI, is the standard unit for mass. Okay? We don't usually use a mass unit in U.S. customary. We always talk about weight. That's not very precise or accurate, but we do. The main reason they showed this is just to show the similarities between the equations. Force, this is net force up here, that's the acceleration of the body. Down here, weight is your force due to gravity. Mass is the same, and the acceleration associated with weight is the acceleration due to gravity, whatever gravitational field you're in, which for most of us, our whole lives will be the Earth's gravitational field. Okay. Now, I think where we left off, I think we went over all that. So let's do example 210, and 211, which use that principle of weight. What is the weight? So here we're looking, whoa, let me get my pen. What is the weight? Little w is what we use to represent weight, in this text anyway. Teaching another physics class on Wednesdays, that book uses F sub w, okay? Different books use different things. This book is using little w for weight, okay? What is the weight? That means that's the unknown here. Of a 60 kilogram person, what's 60.0 kilograms? What's that a measure of? I'm sorry? Mass, perfect, okay? On the surface of the Earth. So if it's on the surface of the Earth, what acceleration do we use?
9.8.
Yes, g is equal to 9.8. You can put 9.80 meters per second squared. Now, why did I choose that one and not the other one? Yes, with the SI system, where we're using mass in kilograms, we use the acceleration due to gravity in meters per second squared. If we were using weight of pounds, then g would have to be, you want to remember? 32 feet per second squared. Perfect. Okay. So what formula or equation relates these three quantities? It's on the previous slide.
Weight equals mass times gravity.
Weight is equal to mass times acceleration due to gravity. And that's what we're looking for is the weight. The mass is 60.0 kilograms times 9.80 meters per second squared. And here's Mendez. Okay. Just a moment here. Everybody had completed the first lab, or last person turned it in at the end of lab last time. So, now, you probably need your second lab too, don't you?
Yeah.
Okay. You'll need to get with somebody and get the data. It's going to be kind of hard to pull it just off of the recording because each team was recording its own data. So that's certainly what it's saying at all. Or if you want to get with me sometime, maybe after lab today, you might be able to get those data done then. It's going to take a little bit of a while, but we could maybe do that. Or sometime other during my office hours. Okay. Same for you, Amanda. All right. Did anyone make the calculation here?
It's 588.
588 what? Newtons. Kilogram meter per second squared is a newton. Okay, 588 newtons. Now, the book did something a little differently. And here's what they did. They did not put the 0 as an extra digit on acceleration due to gravity. And since they didn't, this only has 2 significant digits. This has 3, but that has 2. 3, 2. So this one can't be any more than 2. So you round that to count 1, 2, look to the right. That's a 5 or greater, so you bump up the previous one. 590. You have to put a 0 there for a placeholder. Newton. You put either one of them, that's fine with me. Okay? But generally don't put a whole huge string of decimal places if you can only support 2 or 3 significant digits. But something like this, either one of those is fine. All right. Any questions? Make sense? All right. All right. Okay. We don't need this anymore. I want to make sure. Some of these questions refer back to the previous one. I want to make sure this was not one of those. Okay. Example 211. And this is why I was looking. A 60 kilogram person. What's that a measure of? That's a measure of mass. Okay. Weighs 100 newtons on the moon. So that's a weight equal to 100.0 newtons. Now this is on the moon, so I'm going to put W sub m. What is the acceleration of gravity on the moon? So we're looking for G sub m. Not the acceleration of gravity on Earth. We know what that is. It's a constant. What is it on the moon? How would we do that? What formula would we use?
We start with weight equals mass.
W is equal to m times G, as long as everything's on the moon, and that's the man on the moon. Ah, okay, yeah. Okay.
And then divide both sides by mass.
Yes, since you're looking for G, let's divide both sides by mass. And that wipes out the masses over there. So now you have 100.0. Now, I suggest that you write Newton in its basic units. What are the basic units for Newton? Kilogram, meter per second squared, and divide that by your mass of 60.0 kilograms. And notice the kilograms go out, and what does that leave us? You can actually divide out some zeros too. 10 divided by 6, you can almost do that in your head. That's 1, and 6 are going to 6 point. They're either going to be 17 or 16.7. What units?
Wait.
Oh, yeah, 1.67. Sorry about that. I put my decimal in the wrong place. So it's either 1.7 or 1.67. What do they do? Oh, they do 1.67 meters per second squared. Okay. Way less than the acceleration due to gravity on Earth. Why? The moon is much less massive. Remember, this is all has to do with inertia, and that has to do with the mass. The moon's mass way, way less than the mass of the Earth. Now, for those who are in Physical Science 1 or have been in it before, you probably remember that we have the largest moon. Earth has the largest moon relative to our planet size of any planet in the solar system. Jupiter has some huge moons, but Jupiter is gigantic. So it's proportional to the size of the planet. Our moon is the largest, but it's not the largest moon out there. It's probably only like the 6th or 7th largest, but boy, is most of the other ones like Mars' 2 moons, piddly, nothing compared to ours. Okay, and most of the moons of Jupiter and Saturn are much less than ours. Not all of them, but most of them. Okay, 1.67 meters per second squared. Any question? Difference between weight and mass. It's an important concept. Be sure you get it down. All right. That said, then there was a guy riding his bike, remember? And there was our formulas. Now we're ready for Newton's third law, page 45. Okay? Newton's third law of motion. Now this is somewhat different from the other two. If you remember the first one, the motion, think of that as velocity, of an object is constant. It does not change unless there's some unbalanced force acting on it. The motion, if it's at rest, it stays at rest unless something makes it move. If it's moving, it moves in a straight line path unless something makes it change its motion, like a force, net force, unbalanced force. Okay, the second law was if there is an unbalanced law, that body then will change its acceleration. Either speed up, slow down, change direction, do something like that, that will accelerate, change its velocity. Now, both of those dealt with a single body. Okay? A body is at rest. A body has a net force acting on it. Yeah, a body. Newton's third law deals with pairs of bodies. Okay? The source of the force, okay, are other objects. And I think I've read somewhere that Newton described it this way. I don't have a rock in here. But he said, if I push on the rock pushes back on me. I'm pushing on the corner of the desk, and sure enough, it pushed back on my finger. So it's a dent in it. It'll come back maybe. Okay. So you're always dealing with two different bodies. So the third law relates the forces between objects. Okay? And here is an expression of that. Whenever two objects interact, the force exerted on one object is equal to, but opposite in the direction, because remember forces are vector quantities, opposite in the direction of the force exerted on the other object. Okay? So if I was pushing on this desk with a force of 10 newtons, then it's pushing against my finger with a force of 10 newtons. Okay? Whenever two bodies interact, the force exerted on the one is equal in size, opposite in direction to the force exerted on the other. I don't know if any of you have ever seen probably on YouTube videos or somewhere, slow motion shots of something happening with a sports object. For instance, someone hitting a tennis ball with a tennis racket. If someone has taken a very high speed, I guess you say, film of that, picture of that right when the person strikes the ball, okay, you'll see that the ball flattens out against the racket, and the racket bulges back in the back. The racket's acting on the ball's acting on the racket. The two forces are equal, but opposite in directions. This applies, believe it or not, to someone hitting a baseball with a baseball bat. If you took a picture of that right at the moment of impact, you see the ball literally wrapping around, not all the way around, but wrapping, being indented by the bat, and the bat, if you could see it, is covered by the ball, it would be sprung back ever so slightly. Okay? Not break. That's why if you hit it wrong, it breaks the bat. You've probably seen that happen in professional sports and maybe in others. Okay? Golf. If you've ever seen when someone hitting very hard with a driver, say, the ball with the club, you'll see the ball actually flatten. That hard old golf ball flattens against that head of the club, and the club, you can, if you look at it carefully, you'll see that bends backward and then springs forward. Every time it comes back to the original shape, we call that elasticity. tennis ball, the tennis racket, the golf ball, the golf club, the baseball, and the baseball bat, they all come back to the original shape. That's because they're elastic. They return to the original shape. But they are deformed when it's interacting. And that's an evidence of two objects interacting. Now, I have a dumb example of that. When I was in college, both as an undergraduate and generally in grad school, though I had less time in grad school, but I did. At the University of Georgia, when I was working on my master's, I was a group of us had gotten together a co-ed volleyball team, okay? And we had this one tall gal who had played in high school. She was pretty good. And actually, her best friend was her setter in high school. And she was really good. So we thought we had a pretty good shot because we had, two females that were quite good at what they were doing. And we went to play one evening in the gym, and we got there, we were knocking the balls around some, warming up, and we saw the team we were playing. And they had a really tall gal. And we just watched her a little bit. She was really good, okay? And she had this friend who was excellent at setting her up, too. And went, uh-oh, we have been counterpunched with the same weapon, okay? And in the course of the game, this gal was good. She was a spiker and a half, okay? And if you know about volleyball, when you're playing it properly, each team is rotating, but kind of in opposite directions. So you always are going to wind up right across from every other member of the team at some point, okay? And when it came my turn to be on the side exactly opposite the spiker on that side, I knew all I could do was when we served to them and that gal got under it and set it perfectly for this guy, all I could do was get up. Oh, and by the way, before we get there, have y'all played real volleyball before? Okay. You know those are not softballs. Now, they're not as hard as a baseball or a golf ball. Not anywhere close to that hard. But they are not soft. They're harder than a tennis ball, I think. Would you say? So when they're pumped up with air, they're there. Okay? So, anyway, here I go. I know it's coming. So all I can do is get up and make as big a surface area as I could to try to get the ball to bounce back on the other side. Well, she came down with the spike. As I was going up, her spike came down, hitting square in the face. Okay? Now, and this is the truth. I felt the ball touch each ear at the same moment. Okay? That ball deformed around my face, exerting a pretty good force on my face. And what solace I had that my face was exerting the same force on the ball was absolutely none, but that was true. All I saw was Wilson, but no, I'll just make that part up. But anyway, that was the experience of balls being deformed. Newton's third law. I've experienced it in person. Okay. Boy, that wasn't much on Newton's third law, was it? Okay. There actually will be, once we start talking about momentum, an example of that third law, and you'll see the pictures in the book, but we'll get to it in a little bit later. Okay? Because Newton's third law is fairly closely associated with the concept of momentum. Now, momentum is a brand new quantity. Okay? It's a little bit like a force, but not the same. How it's similar, they're both vector quantities. Okay? They both depend on mass. Okay? But what's the difference? Okay, we'll say that's force. What's the equation for force? Formula for force? Newton's second law? Boy, that's an important one to remember. Yes, F equal ma. this is P is equal to mv, okay? Now, why they use P for momentum, I'm not sure. The best guess I could make is when Newton was writing about it, of course, he wrote in Latin. All science was done in Latin. No one spoke Latin except the church people, but all science was written, all academic stuff was written in Latin. And so my guess is the word he used for momentum in Latin probably started with a P or a rho or something that looked like a P. Okay. That's my guess. Well, I'm not sure on that at all. But anyway, linear momentum, the symbol is P. Okay? Now, they say this is in part or properly closely related to Newton's second law because it's so similar. Newton's second law says force equal mass times acceleration. This says momentum equal mass times velocity. Velocity is a vector quantity, momentum is. Acceleration vector quantity, force is. Okay? Both depend on mass. Mass is a scalar quantity, no direction associated with it. Okay? Now, a little bit more, and this is, okay, I don't read Latin, okay? Never have, never will, probably. And, but what I understand, Newton, I think very seldom even talks about forces. I don't know for sure, but I'm guessing he does. He didn't really talk about mass that much. What he talked about was the quantity of motion. And what did he define as the quantity of motion? The product of an object's mass times its velocity. Its momentum. I'm not sure he used that word. He called it the quantity of motion. Okay? Now, so both of these things are involved. The motion of the object is velocity. The inertia of the object is mass. Okay? Now, think about his three laws again and how much simpler they would be if you used his quantity. And this is probably what he used to describe it, his quantity of motion. He would say, for the first law, an object's quantity of motion does not change. Period. Okay? If the velocity is zero, it stays zero, unless it's acted on. And this he probably did use an unbalanced force or something like that. But the quantity of motion does not change unless it's acted on by an unbalanced force. Actually, probably the way he referred to that, there's another term. In an isolated system. Isolated system can't have unbalanced forces acting on it. That's probably how he referred to it. But think about the second law. The quantity of motion is, better than that, the force is the time rate of change of the quantity of motion. What did I just say? The time rate of change of the quantity of motion. What does time rate of change mean? If you're changing the quantity of motion over change of time, right? Time rate of change of the quantity of motion. Okay, does mass change? No, it's an invariant. So you can pull that out of the delta because it's not going to change. What do you have left? Mass times the change of velocity over the change of time. And guess what the change of velocity over change of time is? Please note. Huh? Acceleration. This is where you get ma. This is probably exactly how Newton referred to it. The time rate of change of the quantity of motion. Rather than calling it mass times acceleration, time rate of change of this, and that was your net force. So no wonder they say it's related to this. Okay? Both of those being vector quantities. Okay. So, Newton's second law, if there is a net force acting on an object, the time rate of motion, that is the, okay, let me get this right. If the time rate of change of an object's quantity of motion is changing, that's what you define as a net force acting on the object. Or something to that effect, okay? And then the third law, the time rate of change of a quantity of motion is equal for two objects interacting. but in opposite directions. I mean, so much simpler to express by this quantity of motion. Okay, let's see what else is on this slide. Oh, here we go. I knew it was going to show up somewhere. Let me get my ink off of there. Here is the figure I was talking about from page 45, I think. No, this is the one on page 47. Very similar to the one on 45. Okay? So let's back up for a moment without the information down here and just think of Newton's third law. Here is an astronaut touching a satellite out there in space. Now, you better be careful, or she better be careful. If they exert too much force on it, it's going to change its velocity forever. Okay, remember, outer space, there's nothing else to make it change back. So if this person pushes on that a little bit, it's going to speed up and go, but this one is pushed back. Newton's third law. Equal and opposite forces acting on the two bodies. Now, if this body was more massive than that body, then this is going to move faster, this will move slower, because the forces are equal and opposite, okay? But if the two masses are the same size, they'll move apart with the same velocities and accelerations, okay? If this object is more massive than this one will move faster, that will move slower. The net force is the same. Okay. Now, let's get to our figure here as given. Is this actually, yes it is. This is example 212. Okay. Now on page 46, and that's where the example is, on page 46 you see some football players. I don't know if they look like high school to me, but maybe they're college, I don't know. I'd say high school, okay? And different place. We're going to have an example that deals with football players, but this isn't the place, okay? Still, it's talking about you see the quarterback there, pivoting on one foot, pushing against the ground. He's pushing against the ground pushes on him, he changes his direction. Pivot makes him change, okay? He was going this way, he's going to turn and come back. This guy that's supposed to be blocking doesn't look to be doing much of anything. Never mind, we won't get into that. Okay, so let's do example 212 on page 46. A 60-kilogram astronaut, that's this right here, okay, is freely floating in space and pushes on a freely floating 120-kilogram spacecraft. So this is the mass of the spacecraft. The spacecraft more massive than the astronaut. Doesn't really look like it. Must have some pretty dense material in it. Okay? He pushes on this freely floating, it's hard to say too fast, 120-kilogram spacecraft with a force of 30 newtons for 1.50 seconds. So they don't list that anywhere here. So the force of astronaut on spacecraft is 30.0 newtons, and the time interval over which he pushes is 1.50 seconds. Okay? The question is, compare the forces exerted on the astronaut and on the spacecraft. We're just told the astronaut pushes on the spacecraft with a force of 30.0 newtons. Now discuss what's the force that the spacecraft pushes on the astronaut. Is it pushing on the astronaut? Sure, Newton's third law, it's got to. How much is the force?
30.
Yes, just in the opposite direction. So this guy or gal is pushing this way, the spacecraft pushes exactly the same. The force of spacecraft on astronaut is also 30.0 newtons. And if you want to be technical about it, that would be a minus 30 because it's in the opposite direction of the first. Okay? Make sense? Okay. That's the A part. The B part. Compare the acceleration of the astronaut to the acceleration of the spacecraft. Okay? Well, now we're looking at acceleration of the astronaut versus acceleration of the spacecraft. What relates the mass of the astronaut, the force of the astronaut, now this is the force on the astronaut, this one, and the acceleration of the astronaut? What formula relates those three?
Force equals mass times.
That's it. Force equal mass times acceleration. Now we're just going to use the magnitude of the force, so we're going to leave off the sign, the minus sign. We're looking for acceleration here, so do you want to solve it literally first, or you want to plug and chug? I don't care much. Which you want to do? Solve for A first, and then plug in the numbers, or plug in the numbers first, then solve for A? Which you want to do? You choose. Plug in the numbers first. What do we know the force is? Absolute value? 30. 30.0. And rather than newtons, let's write the basic units. What is a newton? Kilogram.
Or times meters over a second.
Meter per second squared is equal to the mass. We know the mass of the astronaut, 60.0 kilograms. And the acceleration, that's what we're looking for. That's the unknown. So what do we do? What do we do? Not multiply, it's already multiplied. Divide by the 60.0 kilograms to isolate the acceleration, the thing we're looking for. Okay? So you divide both sides by that. That would be 30.0 kilogram meter per second squared divided by 60.0 kilograms. And what do you get? Kilograms cancel out. 30 divided by 60 is 0.5, but we have three significant digits, so we'll put 500, all three significant digits. The kilograms go out, so you're left with meters per second squared, which is an excellent unit for the acceleration of the astronaut. Okay? 0.5 meters per second squared. And the sad news is he's freely floating in space. Doesn't look like tethered to anything. There he goes. Bye-bye. Okay. Nothing to stop him unless somebody comes out there and stops him, or he's tethered to something somewhere. Okay. All right. It says, compare the acceleration of the astronaut to the acceleration of the spacecraft. Let's do the same thing for the spacecraft. Same formula. Force of the spacecraft, that would be the astronaut on the spacecraft, is equal to mass of the spacecraft times the acceleration of the spacecraft. Okay? Now, you want to do it the same way? Okay? So we had acceleration of the spacecraft is equal to the force of the astronaut on the spacecraft divided by the mass of the spacecraft. What was the force of the astronaut on the spacecraft? Absolute value? Still 30. 30.0. And what's the fundamental units of force? Kilogram meter, not mass, meter per second squared. Okay, divided by the mass of the spacecraft was and is 120.0 kilograms. Okay, and again, the kilograms go out. They divide away, cancel out, whatever you want to say. And what is the acceleration of the spacecraft? You can wipe out the zeros too if you want to. 3 divided by 12 is? Anyone know? Pretty easy. Help me, somebody. 0.250. What units? Meters per second squared. And it keeps accelerating at that because there's nothing to slow it down. It's out in space. All right. Now, that was just done through Newton's third law. Okay? Not dealing with momentum at all here. It has to do with it, but we're not dealing with it. That was forces, masses, accelerations. Okay? Newton's third law. Okay. Now, just thing of note here, since the forces have to be the same, and forces mass times acceleration, double the mass, which this was, twice the mass of him, you have the velocity. Ooh, this is a different problem here. Don't worry about that. You half the velocity, not acceleration, I don't know what, acceleration. Half the acceleration of what that is. Because if you, this is half the mass, so it's twice the acceleration, twice the mass, half the acceleration. So it works that way. Linear inverse relationship. All right. Now, let's do example 2.13, middle of that column on page 47. After the interaction and acceleration between the astronaut and the spacecraft, described in example 212, that's what I left up here, they both move away from their original positions. What is the new speed of each, for each? So now we're going back to speed or velocity. Okay, let's deal with the astronaut first. What would be his new speed? Let's call it his final speed. What was the formula that related speed, maybe initial speed, acceleration, and remember we had that little quantity of time in here. Anyone remember the formula? Well, say again? Oh, y'all used it enough in lab, I thought you'd have this down pat. What did you use in lab? Well, maybe not exactly. Yeah, you did at the very last. Acceleration was change in velocity over change in time. That last column you did, remember? That was your acceleration.
Velocity acceleration times.
Yes. Actually, a little more formally, initial velocity plus the acceleration due to times time. Okay? But what was your initial velocity? 0, because they were both, if you go back and read the problem, a 60 kilogram astronaut is freely floating in space and pushes on a freely floating spacecraft. Okay, so they're not initial velocity, they're just there, 0. Okay, so what would this be? Acceleration for the astronaut? 0.500 meters per second squared times, what was the time interval? 1.50 seconds. Now this second will cancel one of those seconds out and leave you with a final velocity of 1.5 times 0.5.
0.750.
750 meters per second, an excellent unit for velocity or speed. Okay? How about over here on the spacecraft side? Now we're looking for the, we're not, I'm not sure I'm doing the right problem. Oh yeah, okay, I was looking at the wrong one. What is the new speed for each? So yeah, this is final velocity for the spacecraft. And again, its initial velocity is 0, so this is just like you said, a times t, but a for the spacecraft. And what would that be? What do we find that to be? 0.250 meters per second squared times that same time interval, 1.50 seconds. Now you can easily almost imagine that. The astronaut's there, and he goes to push on the spacecraft. 1.5 seconds is all he pushes. It goes this way, drifting off slowly. He goes this way, drifting off slowly. What was his final speed?
0.375.
375, what units? Meters per second, because the second cancels one of those out, meters per second, which again is an excellent unit for velocity. Okay? And you see again, twice, and here we got it. Okay? What, 0.375 meters per second? This is 0.750 meters per second. Okay? Okay. Now, with all this in mind, now let's look at our momentum of these things. Now that we've got the mass of the astronaut, we've just calculated the velocity of the astronaut. What is his, let's start this. What was his initial velocity before he pushed? Initial momentum before he pushed? 0, because he had 0 velocity. Even though he had the same mass, he had no velocity, so his momentum was 0. How about for the spacecraft? 0. Okay? So the momentum of the system of the astronaut and spacecraft was 0. Okay? Now, he pushes on the spacecraft. Newton's third law pushes on him because it has inertia, pushes back on him. Not with a force, but sort of with a force. Okay? And now they take off. So what is the momentum of the astronaut here? What is momentum? Mass times velocity. So let's multiply 60 kilograms by 0.75 meters per second. What do you get? Say again?
It's 45.
45.0. Now, notice the units for momentum. Even though this was probably Newton's quantity of motion, it seemed like to me it would have only been fair to name that the Newton. But no, we made a force a Newton. So we don't have a name for this one. It's just kilogram meter per second. That's all. Well, there is another name we'll come up with in just a couple slides. But that's it for this one. Now, that was in the, say, which way were we say? Negative direction, because it's going in this way. Remember, momentum is a vector quantity, so it has a negative momentum here. They didn't specify it here, but indeed it does. How about the spacecraft? What was its mass? 120 kilograms. Its final velocity, 0.375. There it is, meters per second. Multiply those two together to get the momentum of the spacecraft at the end, and what do you get? 45. So the momentum, the astronaut has a minus 45, the spacecraft has a positive 45. What was the total momentum of the system after the push-off? Minus plus 0. The momentum does not change. Linear momentum is another one of those invariant quantities. Forces change. Velocities change. Mass doesn't change. Momentum doesn't change. Okay? It's a constant of nature, almost, linear momentum. Now, we'll see in not today's lab, but in Tuesday's lab, we'll see there is a slight other things we have to take into mind, because really there's other forms of momentum. We call this linear momentum. There's also angular momentum. Okay? Some of you are pretty familiar with this. You know what a flywheel is? What does it do? Say again? Yes, it tries to keep the motion the same because it's got a large mass, a long, pretty good distance away from the center of the axle, and it sort of evens out the motion. Y'all probably are thinking in terms of cars. When I think of a flywheel, I think in terms of hay balers, okay? Because you had a big old thing there because you're pushing really hard, keeping the bales packed really tight, but the flywheel keeps, even though you're pushing real hard, keeps the speed just about the same. And it had a big old flywheel on it. Okay. Anyway, that's a different story. I grew up on a farm, by the way. Okay. Now, and sure enough, they got it down here too. The momenta are equal, what they didn't put, they're opposite directions. And since momentum is a vector quantity, then one's positive, one's negative, they add to 0. Okay. And by the way, momentum is item 2.7, even though it's related to Newton's third law, it's its own section here, 2.7. All right, now that gets already to what we're going to cover next. Any questions about this before we move on? Okay. The conservation of momentum. This is exactly what I was talking about. Momentum is a conserved quantity. It does not change. The linear momentum does not change. And here is another example of that. Okay? What we have here is a rifle shooting a bullet. Now, before the trigger is pulled, what is the momentum of that system? 0. Okay? The rifle's at rest, the bullet's at rest. But once that trigger is pulled and it hits that shell casing and ignites the explosive that's in that shell casing by the friction and the compression of that, and that explodes and sends the bullet flying out of the barrel, their total momentum is still 0. Okay? The bullet, its mass, the bullet's mass is not changing, but it's whatever its mass is times its final velocity, which is greatly a large number. But this mass is pretty small. That has to be balanced by the momentum of the rifle in this direction. The mass of the rifle is much more massive than the bullet. Much more. So its velocity will be much less. But there still is a velocity. Now, have you ever fired a rifle holding the butt off your shoulder? Oh, you have. And what did you find? It hurt big time.
Yeah,
Back, what's that?
If you got a scope on the gun, you have a ring on the ring guy too.
Yeah. Oh, yes, did you? Oh, I forgot about that. You could have a black eye there too, couldn't you? And that could hurt even worse than your shoulder. Okay. So what you have to do, and the reason for that pain, and literally, people have come away with big bruises here because of that interaction. And I have heard of people having separated shoulder when it's a very high-powered rifle sending forth a bullet with a very large velocity. And they can be fairly massive bullets, you never knew. Yeah, they can actually physically separate the shoulder. You don't want that happening. So what do you do to keep that from happening? Snug it firmly against you. Now, how does that change the system? You're part of the system. It's not just the rifle and bullet. Your part. Now, your mass is way bigger than the rifle and the bullet. So now there's less velocity backwards. But you're part of that velocity. So hopefully there's no bruising. Okay. So sure enough, momentum is conserved. The total momentum of a group of interacting objects remains the same in the absence of external forces. Remember I told you that was probably how Newton referred to things. Isolated system, no external forces. Okay? Now, applications of this. Collisions. I hope you've never been in a collision, but I imagine some of you have. Have you?
Single car.
Huh?
Single car collision.
Oh, single car collision. Those aren't very good either. Okay? Okay. When I first went to college, okay, entering freshmen had to go up a week early for our orientation, okay? So I had been there for a while, and then right at the end of that week, my older brother, who went to the same school, we both went to Georgia Tech, he came back to school, and his friends came back. He was a junior, I was a freshman. And one of his friends had a car. We didn't have a car. My dad had driven us up there separately because I had to go early. But anyway, one of his friends, Frank Michelle, had a nice car. It was a Z28, I think. Okay, he was real proud of it. And Mike and Frank decided they wanted to go see a movie that night. You know, no school, no homework. You weren't behind yet, so yeah, let's go see a movie. Okay, and it had been playing for a little while. It was opening night, but a pretty good movie. I don't think any of you probably have ever heard of it, but it's a pretty good movie. Easy Rider. Ever heard of it? It's a classic. You probably heard of it. No, never. Okay. Easy Rider. I can't remember. Peter Fonda was the main star, and Jack Nicholson, that I think was one of his first major roles. He had never been that high in ability. Y'all probably don't even know who he is. Okay, but never mind. But anyway, they were the two stars of this. So we were going to see Easy Rider. Boy, this off to college, going to see Easy Rider. This is, yeah. So we were going, but Frank didn't know where the theater was, and Mike, my brother, had just a general idea. Of course, I was in the back seat. You know, Mike was navigating for Frank. So they were getting there, and so they came in the general area, and I think they could actually see the marquee for the movie, but they didn't know where the parking was. And Atlanta is pretty crowded on parking. And Mike said, "There it is." So Frank turned without noticing another car was coming this way. I was sitting in the back seat, and just behind me is where the car hit. Welcome to college. Okay. Fortunately, I wasn't injured. Nobody was injured except Frank's car, of which he was very proud up to that point, was pretty badly injured. Okay. But what did the police do when they finally came? Did we get to see the movie that night? No. Okay. We were outside dealing with that. But what they did, they started measuring off skid marks. Okay. Now, they weren't really going to tell them much, but what they were measuring for, because collisions follow Newton's third law. Okay? It didn't really tell them much. It was sort of rainy that night and things, so it wasn't very good. But if you've ever been in a collision, maybe even a single car collision, when they came, did they measure skid marks? Do you remember?
I flipped over a bubble.
Oh, my goodness. Well, they probably didn't have that many skid marks. Okay. I don't know how they could measure that. But what they do, they measure that. Why? They were estimating the speeds. Okay? Because this will tell you that. Conservation momentum work. Of course, it wasn't going to give them very much good data, but he could tell you weren't going at least this fast. He couldn't say if you're going faster, they were, but, you know, fine. Now, other things, analyzing action and reaction interactions. There's enough actions in that statement, isn't there? Okay, I think I'll save the next examples for later. And this is later. A concept called impulse. Okay? Two definitions here. One's on one side of the equation, one's on the other side. One definition for impulse is a force acting on an object for some time interval. I like to call it delta t, meaning it's a time interval. It's not some time a day, it's for some time interval over which it acts. The other side of the equation, an impulse produces a change of momentum. Okay? An impulse produces a change of momentum. Okay. Now, if you remember my earlier expression of what I thought Newton really was saying, he said that a force is the same as a time rate of change of momentum. All we're doing now is moving the time over to the other side. So what we have here is F times the delta t is equal to change of momentum. Delta meaning change in, difference in momentum. That's almost the same formula we had before, except we had the delta t under here. Remember? So see, these are so closely related. But either side of this is called an impulse. Now what's the unit for this? Momentum. That's kilogram meter per second. What would be the units over here? Unit for force? Newton seconds. So there's another unit for momentum. If you don't like kilogram meter per second, you can call it a Newton second. Both of those are legitimate units there for momentum. Okay. Now, as Mr. Garland Corley used to say, the old guy that went to the same church we did, he used to say, when I was a boy child, and I'll use the same term, when I was a boy child, I remember cars, and typically the dashboard of a car was steel. Okay? Steel. Painted maybe, but that's it. You know what they called the passenger seat back then? The death seat. Because if there was ever an accident, that passenger was either going into the dashboard, which wasn't going to give any, or into the windshield, which might break a little bit, but then it can cut you up pretty badly. So in a very serious, like flying over a fence or something like that, pretty bad shape. I'm hoping you had a seatbelt on, did you?
No.
You did.
I'm held on to the steering wheel and still sitting upside down.
Okay. I hope you didn't have a passenger, did you?
I did.
You did. How did they come out?
Oh, that's sitting on the roof.
Oh. Okay. Was it a convertible? Okay, never mind.
No,
Well,
we just flip. This is sitting there to cross out. So I'll sit upside down. So you gonna open the door? Yes.
oh my. Okay. All right. But when I was a boy child, that was the situation. If you hit that dashboard, so let's say the car was going at nameless speed, 60 miles an hour, and you came in contact with a tree. I thought when you said a single car thing, maybe it hit a tree. I think you were lucky not to hit a tree. Okay? But hit the tree, suddenly your change of momentum was pretty great. Wouldn't you say? Change of momentum going from 60 miles per hour with whatever mass that car had to 0 miles per hour. So think how massive that car was. Kilogram, meter per second. Yeah, that's going to be a big change of momentum to 0, because when it hit the tree, it's going to stop. Okay? Now, let's think on the other side. The time interval over which you interact with that dashboard is pretty small, like 1/1000th of a second or something. Can you imagine how great that force was? Hardly any bone unbroken. Okay? Not good. Now, I remember, it may have been, I'm going to sound like PWT here, but we were pretty close to it. Y'all don't know what that means either, do you? Never. Okay. Up to that time, all our family had were pickup trucks, okay? And the 5 of us going to church in the front seat of a pickup truck was sort of like the Beverly Hillbillies, sort of. Not quite, but y'all don't even know what Beverly Hillbillies are. Never mind. Okay, you remember. Okay. But anyway, finally, I think it was the first car my family owned. My uncle had a car that he let us drive on trips and stuff. But when we finally had a car, it had padded dashboard. Okay? Not much. It's still steel underneath it, but probably about an inch, 3/4, something like that padding on the dashboard. That was a big safety feature. Okay? It wasn't a new car, it was a used car. We never got new cars. Okay? For a long, long time. Okay. But anyway, when we got that, what did that do for you? You hit the tree at 60 miles per hour, you're going to have the same change of momentum, but guess what on this side?
You're going to hit the dashboard, you're going to hit the foam before you hit the metal.
Yes, and it's going to take a certain amount of time for the foam to compress before you hit the metal. And that time that it took, maybe from 1,000th of a second to 100th of a second or 1/10 of a second, it's going to take a little bit longer. The force goes down by 10 or 100 times. That was a pretty big deal. Okay? Now, next thing, this was probably 2 or 3 cars later. What did they finally install in the car? Seat belt. Exactly. Now, when I say seat belt, it was literally a seat belt. Okay? No harness type thing. A seat belt. And what did that do to you? Yes, and therefore you went forward, but it pulled you back. So now the time, you may still hit the dashboard, depending on, how close you were to the dashboard and that kind of stuff, but the time it's going to take you to get there is greatly increased now. Maybe even a second, or something like that. Maybe more, okay? So same change of momentum, greater here, lesser there. The force is going to be less, okay? Now, what do they have? Well, then they put in the strap on top that held you even more than just choking you at the waist. Now it holds you this way too. Still gives, may even break in a real serious collection, but at least it's going to slow down, so your force is even less. Same change of momentum, greater time interval, less force. And now they have airbags. That's what they're talking about here. Airbags, if they deploy correctly and blow out there, now you hardly ever touch the steering column or the dashboard. And the dashboards aren't made out of steel anymore too. That's another feature. So quite often people can go through some pretty serious crashes and not have any injury at all. Really shook up, really upset about the car, but no major injury. Okay? Because you've increased the time interval and decreased the force. Okay?
Yeah, my truck I had, it was a dud. Because none of my airbags went on. Nothing.
Well, you didn't really come to a sudden stop, did you? Till you hit the ground.
It came to a sudden stop. My A-pillars and my roof was like sitting on my seats.
The what was?
My A-pillars
Oh.
in front of my doors, they was like big flat.
Oh my goodness, yeah. But that was the side.
No, it was on top. It didn't
On top.
No side impact.
Okay, but you see, there's no airbags on top. It wasn't, if there had been front impact, it may have come out.
But no, it's just straight on top.
Yeah.
Check these things out, I'd have had it converted.
And your friend was sitting on top too. Yeah. All right. Was he there before the collision too?
Yeah.
Oh, I see. Okay.
Yeah, we wrote the whole thing together.
Okay. All right. Good deal. All right. Now, we talked about football players before. What's the big concern about football players these days? Yes, and other serious injuries. And those helmets, they have the straps in them that absorb a lot of that, increasing the time interval, decreasing the force. They have padding in there, increasing the time interval, because there's some pretty big changes of momentum happen when people. What is the serious injury serious violation they're called and get you kicked out of the game? Targeting. Because and that's going in with the head, generally at the head. They're trying to end that. minimize it, okay? And there's a reason for that. There's pretty serious injuries coming out of that. And I've also noticed every offensive lineman I've seen in college football, I think in the pros too, they look like have polio or something. They have braces all up and down here.
Yeah, they keep their knee braces on. Yeah,
Say again?
knee braces.
Yeah. That I'd never seen that when I was in high school and college, you know. And there were a lot of people with
They do that now. They do that now to protect them from knee injuries.
Yeah,
They get
exactly.
swallowing and stuff.
Yeah, and that because that absorbs and increases the time interval over which that hit happens, and keeping your knee from being the thing that absorbs that. Okay. So that's why paddings. There are also shoulder pads, knee pads, thigh pads, all those pads in there. That's the reason to increase this, so those changes of momentum you hit reduce the forces that your body has to absorb. Okay. Now, you can tell this is getting a little dated. They do use plastic barrels on highways still, especially when they're doing construction or paving or something like that, because when cars come along, that's not going to damage the car as much because it takes those things longer to collapse than and decreases the force. Yes, and they quite often put stuff in them, like a new sand. I hadn't thought they'd probably put water in them. Yeah. And I guess that's, so what do they do? Have a tanker truck come along and they put them out and then fill them up later? Okay, I've never seen that happen, but yeah, that makes sense.
Corners of your highway and you got split off, they'll run like a base shape.
Right.
So if you hit one, it's like bowling ball thing.
Right. Okay, and all that is doing is increasing time interval, so it decreases the force. Now, what have they started putting now? I can remember not too many years ago, several interstates still have them, these concrete dividers to keep cars from this lane going over there. What do they use now?
The wires.
The wire rope,
Yeah.
and stanchions. And those stanchions are basically bolted there. So if someone hits them, they go down. But that's increasing the time interval, decreasing the force. You hit those concrete pillars, the time interval very small, the force very big. So there's that. Now this is another, and this is pretty sad, but it's true. One of the big sports in the Summer Olympics is gymnastics, right? Isn't that summer? Pretty sure that's summer.
Yeah, it's in summer.
Okay, and when the Summer Olympics, and y'all may not remember this because y'all probably weren't born then, 1996, and okay, they were in Atlanta, Georgia.
Yeah, they got bone.
What's that?
They got the bone in half again.
Yeah, there was that bomb thing right there. Did they actually find the bomb? I know there was one didn't go off, did it?
No, one didn't go off.
It did go off.
It did go off.
Yeah, they got the guy who did it.
Yeah.
Yeah.
Okay.
Did go off.
Yeah. Were there any fatalities with that?
Yeah.
Okay. It was pretty sick. Huh?
There's a park here now.
Yeah. It's the Centennial Park, I think it was called. Why Centennial? That was that. Yeah, and they had, yeah. And it was pretty close to Georgia Tech campus, but I was long gone from Georgia Tech campus by that time. But we did get to go to the Olympics to see a tennis match or two. That's all. But we saw that part that was before the bombing. Okay? But we didn't see the gymnastics. But one of the young Chinese girls, especially women, but I swear some of them were so young, it's just unbelievable. But anyway, one of their events was running down this runway just as fast as she could go and hitting what you call that? Vaulting. That's what it's called. Whatever that thing she vaulted off of, and then doing some sort of really complex twisting and turning but she got off a little bit and landed on the gym floor because everywhere else was padding. The padding increased that time interval, decreasing the force of the landing, but she hit the gym floor, which the time interval was very small, the force very large. I'm pretty sure she's a quadriplegic. At least a paraplegic, I believe a quadriplegic. That the body cannot take that. And that's why every one of those events, you have just stacks and stacks and stacks of padding. The high jump, the pole vault, you know, stacks and stacks of padding. The parallel beam, stacks of padding. Even the floor exercises, look at that floor, how much that gives. I don't know what they do to that, but it gives a lot. Okay? Because they're trying to increase that time interval, decreasing the force that the body has of sort. Okay. Probably beat that to death, didn't we? That's impulse. All right, and here's the same equation I just did. We did before. Force is change of momentum over time. I like to put delta t down here. That's initial minus final times t. That's if the final momentum is 0, like you hit the tree or whatever it is you hit, then this is a minus pi over t. The larger the time, the less the force. The shorter the time, the greater the force. Okay. I like this formula better. It says it better than that. But it's same formula. All right. That was impulse. Oh! We missed a couple of examples. I didn't turn the pages in time. Let's go back. We'll do it here. And let's do, got too many stories. Example 214 on page 48. A 20,000 kilogram rail car. Okay? Now I don't draw rail cars very well, so don't laugh, okay? Okay. This rail car is 20,000 kilogram. What in the world does that measure? What does kilogram measure? Mass. That's the mass of the rail car. Okay, is coasting at 3 meters per second. What's that a measure of?
Velocity.
That's your velocity. Perfect. Okay. Going pretty slow. When it collides with, now here is it has a coupler here, and it collides with another rail car sitting here. Ugly, ugly, ugly. Okay. Identical rail car. So its mass is also 20,000 kilograms. Okay. Collides with a second identical car at rest. What does that mean? Say again?
0.
Its velocity, initial velocity, this is a rail car 2, is 0. This is the initial velocity of rail car 1 is 3 meters per second. This one's at rest. Now this also has a coupler on it, you know, whatever. Okay. Now, what is the resulting speed of the combined cars? Okay. Now, when they say it collides, it says, okay, resulting speed of the combined cars. That means those couples link together and they go together. Okay. So this is your initial situation. Here's your final situation. This is going to be even worse. Especially since the rail is going uphill here. They've linked together here. So what's the initial momentum of this car 1? Initial momentum of car 1. Okay, that's its velocity, but momentum is Momentum is mass times velocity. What's its mass? 20,000 kilograms. And its velocity? 3 meters per second. So what's its initial momentum? 60,000. What units? Kilogram meter per second. You have to use all the units there. Kilogram meter per second. We don't have a special unit for momentum. Closest we got is a Newton second, but we're not dealing with those now. What's the initial momentum of car 2? 0, because its velocity is 0. Even though it has 20,000 kilograms, still has no velocity. So what's the initial momentum of the system? 60,000. 60,000 kilogram meter per second. Now, they collide, they link, and they roll away. What's the final momentum of the system? Momentum is conserved. So what's the final momentum of the system? Same as the initial. It's conserved. There's no external forces here, so it's conserved. Final momentum of the system is also 60,000 kilogram meter per second. Now, what is the final mass of the system? They've linked together now.
40,000.
Now this mass is 40,000 kilograms. So what's the final velocity of the system? What you reckon that would be? Or what relates those together?
You divide it.
Yes. P is equal to mv. If you're looking for v, divide both sides by m. Okay? So this will be final momentum of the system divided by the mass of the system. Final momentum was 60,000 kilogram meter per second divided by the mass of the system, 40,000 kilograms. Kilograms go out, and all these zeros go out. And what's 6 divided by 4? Oh, using a calculator for that? 1.5. Final velocity of the system, 1.5 meters per second. Now, here's where the book gets a little squirrely in my mind. Okay? This is only one significant digit here. It could have been 2, 3, 4, or 5, but it's only one. The 2 is the only significant digit. 3 is the only significant digit there. Okay? 60, those are fine, one significant digit. 40, that's fine, one significant digit. So they write their answer with one significant digit. And what do they write it as? They look to the right, see a 5, they bump it up to 2. That makes no sense. Put it 1.5. It's half what the initial velocity was. Don't go around rounding off there. That's literally, in my mind, stupid. Okay? Yeah, it's using significant digits, but that's a rounded quantity. Okay? The actual is about 1.5. Put it 3 halves. That way you don't have to put any decimal in it. Okay. Now, that was example 214. Let's do 215. That doesn't relate at all. You don't use any of this. So now we've got a student and her rowboat have a combined mass of, so here's the water, here's the rowboat in the water, and here's the oar in the rowboat. Doesn't look much like an oar, okay? Something like that, okay? Student and a rowboat have a combined mass of 100 kilograms. So the mass of the boat and student is 100.0 kilograms. They told us that. standing in the motionless boat, which is usually not a good idea, okay? Okay, she's she, so I'll try to make it look like one. Ooh, ugly, ugly. Okay, standing in the motionless boat in calm water, here's what's happened. She lost her rowboat, her paddle, and she's sitting there. Absolutely no way to move, okay? But, clever that she is, she happened to carry some rocks with her. Of course, I always carry rocks in my rowboat, okay? So what she does, she gets a rock, and this is a 5-kilogram rock. Okay, a 5-kilogram rock. Probably put it in the wrong hand. Oh, never mind. Okay. And she throws it out the back of the boat with a velocity of 5 point. Velocity. Let me start that one over. That came out really ugly. As if any of this isn't. Okay. The velocity here of the rock is 5.0 meters per second. Okay? What would be the resulting speed of the boat? Will it have any speed? What do you think? Yes, because initially, what was the momentum of the boat and the woman and the rocks and everything else? 0. Because it says motionless. A student in a rowboat have a combined mass, blah, blah, standing in the motionless boat in calm water. Nothing's moving. So the initial momentum, Pi of the system, is 0. Now, she throws the rock out the back of the boat. I've got it in the wrong hand. She's going to swing around there and do it. I don't know. Okay? So what is the final momentum of the rock? What would that be? Anybody?
Final momentum of the rock.
Yeah. After she throws it. When she releases it, and it's going 5 meters per second, and it's a 5-kilogram rock. What would be its momentum? 25. I'm going to put a point. No, we don't need a point C. 25 kilogram meter per second. So what do you reckon, and you can decide whether you want that being positive or negative, it doesn't matter to me, does the boat, what would be the resulting speed of the boat? So does the boat have a P final of the boat, the woman and the boat? What's its final momentum? Don't divide anything. Just look at momentum.
25.
It's 25 also, but in the opposite direction. 25 kilogram meter per second. Because momentum is conserved. It was initially at rest. The rock takes off with 25 in that direction. That means the boat has to go 25 in that direction. Momentum. Kilogram meter per second. Okay? And what's the mass of the boat? So this is mass times velocity of the boat, mass of boat times velocity of boat, and this will be 100.0 kilograms. Now, why they gave us that many significant digits there, times V sub B. That's what we're looking for, and that's equal to the final momentum of the boat. And that was 25 kilogram meter per second. So what do? Divide both sides by 100. 0.0 kilograms, 100.0 kilograms. And this goes out here, everything goes out there. The kilograms go out here, and what does that give you? Say again? 25 divided by 100. divided by 100. 0.25 meters per second. So she is heading, hopefully, towards shore now. Okay? That is final velocity of the boat. Now, so hopefully she pushed in the water enough to get her pointed toward the shore, threw the rock in the opposite direction, and sure enough, the boat starts moving very slowly to shore. And, or maybe she's going in the direction of her paddle. Okay, that would be smart too. Okay. All right, good deal. That was all before we started on impulse. Sorry, I got a little ahead of myself. There is on page 49 what they call a momentum experiment. We'll do something like this in the lab on Tuesday. Okay? So we won't worry about that. We won't have the fancy setup, but we'll do something like it. Okay. So that was momentum. That was conservation momentum. That was impulse. All right. Now we're at 2.8, forces and circular motion. Now don't let me go over. We still got, well, about 45 minutes, right? Okay. Now, anytime you feel like you really need a break, we can take one. I don't want anyone uncomfortable or stuff like that. So I know these go awfully long. I can sit up here and talk all day, but you know, y'all are having to be still. I get to stand up and down, you know. So anyway, forces and circular motion. What we mean by circular motion, do you think circular motion is accelerating? Why? Changing direction. To change direction, your velocity has to be changing because velocity is a vector quantity. Even though it doesn't change speed, if it changes direction, you're accelerating. Okay? Now, we call that acceleration, when you're in circular motion, centripetal acceleration. And what word do you almost see in centripetal in the first part? Center. This means center seeking. The acceleration is always toward the center of that circle. That's what pulls the thing around. Okay? If you got a centripetal acceleration, that means you have to have a centripetal force. If there's a mass, and obviously there must be a mass involved too. So a centripetal force must be acting on it. Now, I can remember when I was young, people talked about centrifugal forces. There's no such thing, really. It's an apparent force. It's not really a force. That was the force, remember when we talked about riding on the bus, you know, not hanging onto the strap, and the bus changes direction, and we said you were thrown against the side of the bus? No, you weren't. The bus cut in front of you, okay? You weren't thrown out. That was what they would have been calling a centrifugal force. It wasn't. The bus moved, and you were trying to maintain your motion, okay? So this is an apparent outward tug as the direction changes, but it's not really a force. Your centripetal force, well, this is talking about something else. Think of this as, I'm sure none of you ever did this, tie a rock on a string and swing it around your head. No, you didn't, did you? Yeah, you did. Well, what happened when the string broke? No longer had circular motion, did you? Took off in a straight line and went right for a window. Always it finds a window, okay? Never fails, okay? Now, so when the centrifugal force ends, motion continues in a straight line. Remember Newton's first law? Unless there's some outside force, which was, unbalanced force was the string holding that in place. But it ends and you have straight line motion. Okay? Now, here is an example of this. Pretty example, too. Your motion is in a circle, circular path. You've got a string here swinging that rock around, okay? It's a circular path. The velocity of the rock is always perpendicular to the center, the line going to the center, okay? Always, okay? But this is exerting a force, changing the velocity every time it moves a little bit and that's your centrifugal acceleration. There's your centrifugal force. Okay? Now, the formula for this one. I can't believe they don't give the formula here. Let me back up one so I can give you the formula. It's in your text. If I can get to the right page here. Here it is. The centrifugal acceleration here, A sub c, they call it, is equal to V squared over R. Now, I hope you remember my saying to you sometime in the first two classes, that 3 classes I guess we've had now. Most of the time when you have a square in your variable, you're preceded by 1/2. I said there will be at least one time when we don't. This is it. Part of the reason for that, you actually have 2 variables here. The velocity is one, the radius is the other. So that sort of makes it down to almost like one variable, but it's really not. Okay. And that would be to a single power. But that's your centrifugal acceleration. Now, how would you get centrifugal force out of that? What would be your centrifugal force? Centripetal force. What is a force? Net force? Newton's second law? Earth to class, come in, please. Okay. Come on. One of the most famous formulas in all of science. No, not that famous. Okay. We've hit it several times. Newton's second law. Say again? A little louder. Yes. What was it? Mass times? Acceleration. You answered it before. So you take the mass times this acceleration. V squared over R. There's your centrifugal acceleration. Mv squared. Centrifugal force. Mv squared over R. So, using those, and I'm going to need the space, so I'm going to erase them, but surely y'all have them implanted in your brain now, right? Sure you do. Okay. Example 216. A 0.25 kilogram ball. What's that a measure of? That's your mass, okay? Is attached to the end of a 0.5 meter string. What's that a measure of in that formula we just had? What was your length in that? They called it, told you, implant those in your mind, imprint them. What was that? A sub c was V squared over R, of course, okay? So this is your R. That's what you're swinging around. That's the length of the string. That's the radius of that circular motion, okay? And moved in a horizontal circle at 2 meters per second. What's that a measure of? 2 meters per second.
Velocity.
That's your velocity. Very good, okay? What net force is needed to keep the ball in its circular path? So we're looking for centripetal force. What was that? M V squared over R. Plug and chug here, folks. Mass is 0.25 kilograms. Velocity is 2 meters per second. But what do you do with that velocity? Square it and divide that by 0.5 meters. Okay? Now, let's deal with this. 0.25 kilograms times, what's 2 squared? 4. And when you square the number, you also square the units, so that would be, I've got to sneeze. Y'all awake yet? Okay. You square the units, what do you get? meters squared per second squared, okay, divided by 0.5 meters. Okay, deal with the units first. This meter will cancel one of those meters out. That's good. Now, sort of what do you do next? Okay, now I don't mind decimal numbers too much. When you do 0.25 over 0.5, what would that come down to? It's the same as 1 over if you had 25 cents and 50 cents, what's that a ratio of? How many quarters you got? 1, 2? 2, okay. Now you can do this 2 into that 4 and gives you 2. This is, I don't have a calculator, this is how I do my figuring. And that would be then 2 kilogram meter per second squared. And guess what that is? That's a Newton. So that would be 2 newtons. Your centripetal force would be 2 newtons. Let's see how the book, oh, look at that. They got it right. Good for them.
Shouldn't it be like 2.0 per significant?
Okay, that's a good point, except that this only has one significant digit. This has one significant digit. So nope, we just, we leave it at 1, 2.
But the mass had.
I know, but you go with the least number of significant digits, not the most. Yeah.
Okay.
All right. Good deal. Good try, though. Okay. Now, let's do example 2.7. 17, sorry, 2.17. Lots of examples in this chapter, aren't there? Okay. So let's clear that. I don't think we're using that. Oh, yes, we are. Forget that. Ooh, what are we going to write it? Okay. Suppose you make the string in example 216 1/2 as long, which will now be 0.25 meters. Okay? What force is now needed? So this changes maybe not everything. Oh, I thought I had my eraser up. It changes some things. Oh, we can leave that alone. Okay. So that's going to change the denominator only to be 0.25 meters. 0.25 meters. Ah, this is pretty easy, isn't it? That meter still cancels one of those out. And now your 0.25s cancel out exactly. And what are you left with? 4 newtons, exactly. The centripetal force now is 4 newtons. Half the length of string doubles the force you need, okay? Because it's an inverse relationship. Notice here, force inversely related to the length of the string, okay? So you double the force, or half the length, you double the force. And you probably felt that too. If you had a short string swinging, you're having to hold it a lot tighter, okay? A long one, once you get it going, is a lot easier. Now, other kind of examples of this. I was a weird kid, I admit it, you know, but I always remember, I found it so interesting that if I was carrying a bucket of water, or say a half bucket of water, works a little better, okay? Now, you think I could do the bucket like this?
You don't hold it straight up when you finish.
Say again?
You can swing it and keep it.
Okay, if you swing it, you can have that water directly overhead and not a bit of it spills on it. Why? Because the water is trying to move this way, your centrifugal force is holding it in the bucket still, as you do. Don't stop up here. Okay. That's worse than going over. Not as bad as going over things. Okay. All right. Any questions on that? The answer is 4. Now, notice in the book, though, when we did this to oh, yes, I didn't write this right. That was a 2.0. So I was wrong about that. We had 2 significant digits there. I didn't write it correctly. But when you increase that to 2, this is where they get a little silly. That then makes it that you do put a 0.0 because all your units are now 2 significant digits. That's a 2.0 right there. Okay. So this answer is 4.0. The other one, only 1 because one of your digits was 0.5, only 1 significant digits. Okay. Through with 2.8. Any questions? Now going to 2.9, Newton's law of gravitation. Okay? All right. Gravity is one of those forces, remember? One of those 4 fundamental forces. And gravity is an attractive force between all masses. Believe it or not, my mass, which is significant, is attracting that desk, which has a pretty significant mass too. But you know, I don't feel especially drawn to the desk. So how can they say that? Attractive force between all masses. We'll see. It's proportional to the product of the masses. So my mass times the desk mass, proportional to that. It should be pretty significant, wouldn't it? But it's inversely proportional to the separation distance, squared, okay? Well, this is a very long separation distance, and even if you squared it, that's not a very big number, okay? But notice it says proportional to. That means we have a proportionality constant, okay? That's the key here. Now, later we'll do this last part, okay? And we'll get to this as well. Okay? So let's give the formula here. Oh, yuck. They go straight to the satellites. Okay, let's back off from this and let me give you the formula. They're not putting much on the slides, are they? Here is the symbol. Okay, remember they said the force due to gravity, so I'm going to put F sub g. They don't do that in the book, but I'm going to say that, is proportional to the product of the masses, that's this bullet here, M1 times M2, and inversely proportional to the separation distance, we'll call that R squared. Well, we need a proportionality constant to make that an equality. So we'll say F sub g is equal to, let's see, what can we name that constant? How about capital G, M1 times M2 over R squared? Okay? Well, we need to know what that G is, don't we? All right. And by the way, who came up with this law of gravity? Good old Sir Isaac, okay? Remember the apple? You know, I don't know if that's really true or not. But anyway, that's when he was supposed to have been farming. He was sitting under the apple tree thinking science, you know. I can relate. Well, never mind. Okay. So, actually, they say that in a biography written by a friend in 1752, Newton stated that the notion of gravitation came to mind during a time of thinking that was occasioned by the fall of an apple. So, yeah, that is more than just, I guess, theory, whatever you call it. Yeah, someone making it up. Okay. He was also thinking of why the moon stays in orbit around the Earth rather than firing off. Okay. And so he came up with the relationship of uniform gravitation. Every object in the universe is attracted to every other object with a force that is directly proportional to the product of their masses, inversely proportional to the square of the distances between them. So if the two masses are M1 and M2, this is your formula. Okay? Pretty much as I've written here. The equation gives the magnitude of the attractive force that each object exerts on the other. These are always attractive forces. Okay? The constant G is a universal constant since the law applies to all objects in the universe. Doesn't matter what the gravitational fields or anything else are. It's all, this G is good everywhere. Okay? It was first measured experimentally by Henry Cavendish, another potential paper topic, 1798. So this would have been about 46 years after Newton's biography anyway. Newton was probably dead by then. Okay? The accepted value today is G is equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. What? That's why I don't feel any attraction to the desk. Even though we've got pretty significant masses, it seems like, they're nothing compared to 10 to the minus 11. That's 0.00000000667. That's an awfully small number. Okay, so that's why small masses don't even relate to each other. Okay, I can get within almost touching distance, and I can't feel any attraction. Okay. Now, all right, we're going to get to next to last bullet point in just a few minutes. We're going to do example 218 first. So let me erase this, even though we're going to use that formula. Get it etched in your mind, folks. Now notice at least a person or two has gotten up to go out. Do you need a break? We're only about 20 minutes or so from lab time. What you think? Okay. Because it'll take a little while to transition. Okay, let's keep going then. All right, 218. What is the force of gravitational attraction between two 60 kilogram, that's 132 pound, it's been a long time since I was that, okay, students who are standing 1.00 meters apart. So let's see what that kind of force is. So I'm going to erase what we got here, but y'all remember that formula, right? So what is the force of gravitational attraction between those two students? So F is equal to G, remember what G was? 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay? That was the universal gravitational constant. Okay? And by the way, if you ever forget these and don't remember in the book exactly where it is, look in your text, front inside cover, and front inside cover, very front piece of paper. All know they didn't put it in there. I asked them when they printed these things to be sure. Let's look in the back somewhere. Let's see if they put them back there. I asked them to put it in there. It's something that says physical constants. I don't see it. They didn't put it. So never mind. You'll have to remember what pages they are. Oh, you got it. What page is that? 204? Page 204 in your small books. If you got the big book, it's front inside cover. And see physical constant, it lists several of them. Go down to about the Oh, no, yeah. Number 2, second. Gravitational law constant, also called the universal gravitational constant. G is equal to 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Okay? So, there's that. We're going to multiply that by first one mass, 60.0 kilograms. Okay? And by the other student, who is 60.0 kilograms. Divide that by 1 meter, right? That was the radius, right? Standing 1 meter apart, 1.00 meter squared. Okay? So this is going to be 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times, let's multiply those two together, you get 3600 kilograms squared over, when you square 1, you get 1.00 square meters, you get meter squared. Right? Now notice here, meter squared here, cancels meter squared there. Kilogram squared here, cancel kilogram squared there. Okay? And one will go in the 3600, 3600. So, pull out your handy dandy calculators. Y'all know how to do scientific notation on your calculator? Okay. It's usually something like this, 6.67, and then look for a key that's either EE or EXP. Find that calculator, that button on your calculator. What you got on yours, EE or EXP?
Mine's second for log.
It's what?
Mine's the second one for the log button.
Okay. It doesn't have a name, a thing for it.
No, I pressed the second key and it's above the
Okay.
log key.
Yeah, and then what is the symbol up above the log key? EE or EXP?
It's just 10 to the X.
Okay. I'm not sure that's, I think, no, that's raising, okay.
See it right?
Yeah, I know, I don't think, I've got to get more light. What that is 10 to the, that's not something to the power of 10, I don't think. This is the exponential function that's the inverse of log. Okay.
Well, here, let me show you.
Okay, wait, let me see if I can find what I'm looking for. You may be right. Oh, no, there it is. It's second deck. Okay.
You can clear that.
Huh?
You can clear that if you need to.
Okay. Now, maybe you typed it in right. I couldn't see what you first did. So this would be 6.67, and then the EE, second EE, and then you type in minus 11. That's the shorthand.
Okay.
Okay.
What I did.
Did you
was
put times 10 and then raised it?
7, that to the negative there.
Okay.
So yeah,
Okay.
I think it's going to be the same thing either way though.
No, I don't think so, because that's raising the number 10 to that power. That's not what you're doing. It's 10 to the minus 11. The X there should be minus 11. But do it the way I said, and it will come out right. I almost guarantee. Okay? So EE or EXP, and then minus 11. Now, if you have an old calculator, like I do, it's 11, then you have to change sign, okay? The plus minus key or the CHS key. Those are really old calculators, okay? That gives you that part. Then you multiply it times 3600, okay? And you can divide by 1, but that just gives it to you. So someone do that. 6.67 EE or EXP minus 11 times 3600. And what do you get? Some incredibly small number. Anyone get it?
Is it times?
Second?
Divide.
No, this is multiply. The E or EXP is just which key you hit.
No.
6 point.
111.
Huh?
What's that sound? Behind the 11.
Behind the, oh, that's a time sign. That's supposed to be an asterisk, you know. And it would be divided by 1, but that doesn't change anything. Dividing by 1.
Negative 39,000.
It's what?
Negative 39,593.
Okay, no, something's not right there.
And 33 cents.
Say again?
Not 33 cents.
I'm sorry.
It's negative 39,593 and 3,300.
Okay.
That's what I got.
No. Okay. Let me see how you're punching that in. Okay. 6.67. Okay, now where's your EE or EH? Okay, EE. Okay, then do you have not that minus, that's the problem. You do 11, see that's what's that, 11, okay, and then do plus minus. That changes that. Okay, then times 3,600 equal. That's, whoa! That's not right either. Let's do that one more time. 6.67 EE, and then 11 plus minus, press, and then times, okay, and then 3,600. That's it, I think. That sounds about right. Let's see what the book got. Yeah, that's it. Now, how do you get that? Both of you wound up with something like 0 point, and you had 6 zeros, you said? 1, 2, 3, 4, 5, 6, then a 2, 4, 0, something or other, right? 2, 4, 0 what? 1, 2. Okay. So here's how you resolve that. Since you started with scientific notation, let's go there. That would be moving the decimal 1, 2, 3, 4, 5, 6, 7 places, so it's 2.40. But we only have 3 significant digits, 3 significant digits, 3 significant digits, 3 significant digits. So what we do is count 1, 2, 3, look to the right, that's a 1, throw those away. So 2.40 times 10 to the minus 7th. And what units do we wind up with? Newtons. Now that, folks, is a very small force. That's 0.0000024 newtons. Do you think I'm going to feel that? Nowhere close. Okay? That number here is so incredibly tiny, you have to be a very massive body before you sense gravitational attraction. Okay. And that's what they got there. That's a force equivalent to 5.40 times 10 to the minus 8 pounds. That would be 0.0000005 pounds. I ain't gonna feel that. Okay, nowhere close. No scale in the world can measure that I know of. Okay. Now, let's move on to example 2.19, which is going to tell us how we get our acceleration due to gravity. Okay? So let me delete this. We're going to use the same formula. Okay? But the surface of the Earth, surface of the Earth is approximately 6,400 kilometers from its center. So that is our R. R is equal to 6,400 kilometers. Okay, trouble with that is, what's the SI unit for distance? Not kilometers, meters. Meters. So this would be, you know how to convert that to meters? 3 more 0, because that means 1,000. Kilo means 1,000. So that would actually be 6.4. Now they don't say how many significant digits. I'm just going to leave it like that. Times 10 to the 6th meters. 6,400,000 meters. That's your radius. Okay? From the center. If the mass of the Earth, so mass of the Earth is 6.0 times 10 to the 24th kilogram, 6.0 times 10 to the 24 kilogram. That's a lot of kilograms, folks. A whole lot of kilograms. Then it says, what is the acceleration due to gravity near the surface? Now, let's back off a little bit. I thought they were doing the same thing over here. They're not quite. Oops, that's not what I want. We're going to come back and do that same thing in just a minute. We'll have to repeat that. But here's this. Remember we said force is equal to G times M1, M2 over R squared, right? Now if you're talking about the force on you, that would be your mass times acceleration due to gravity, right? Is equal to G times your mass, that's your mass, times the Earth's mass, because that's what's pulling down on you is the Earth. So that's the mass of the Earth divided by the radius of the Earth squared. So notice what happens. You can divide your mass out. Now, that says the acceleration due to gravity is G, which is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times the mass of the Earth. Now we plug that in. That was 6.0 times 10 to the 24th kilograms. 6.0 times 10 to the 24th kilograms. Okay? Divided by the radius squared. And the radius they gave us was, or we came up with 6.4 times 10 to the 6th meters squared. Some pretty big numbers here, folks. Okay? Now, what you're going to have to do also is break a Newton down to make it kilogram meter squared, meter per second squared, sorry. Kilogram meter per second squared. That's what a Newton is. Okay? And so get rid of the Newton here. All right. One of these kilograms will wipe out that one. The other kilogram will wipe out that one. We'll come back to the rest of the units in a minute. Okay? Let's deal with our numbers first. Okay? You know how to do it now? 6.67 EE negative 11. However you get that. Some of you is 11, change sign, the plus minus sign. Okay? Times 6.0 EE, or 6 EE 24. You don't need a minus in that. Now, when you do a division line, do a divided by, open a parentheses here. You need that because you're squaring. So open parentheses, 6.4 EE 6. Close parentheses, squared, then press equal. And see what number you come up with. And I'll say it one more time slowly. You got something? 9.7705. What? We'll stop there. Okay, now let's look at our units. Here's a meter squared here that cancels out that meter squared, and all we have left is meters per second squared. That's what it says G is. What do we use for G? 9.8. Because here everything, this had 3 significant digits, this had 2, this had 2. So we count 1, 2, look to the right, it's a 7, that bumps the 7 up to an 8 meters per second squared. That's where we get that, is from right there. Newton's gravitational law. Okay? That's where we get the acceleration due to gravity. That's why it says that explains why g is equal to 9.8 meters per second squared. Now, the next bullet there says provides the centrifugal force for orbital motion. All right. Let's just take a look here. That's probably where this slide comes from. And you know what? I think this may be a decent place to stop. So we will stop on this oh, there it is. On this figure here. Once upon a time I had a pencil. There it is. Okay. We'll start next time with that slide right there. All right. Now I'm not doing this too soon, am I? Isn't it 5:45? We're awfully close to it. 5:40? I don't think we can do that in 5 minutes. So let's take a 5-minute break in between. Is what you say?
You won't have a test next time?
No, we won't have a test next time either. I thought maybe if we finished the chapter today we would, but next time we'll finish. Okay, let's talk about that. That'll take part of our time. We'll finish this chapter, which won't take us very long. We only got a couple of pages, probably only a couple of slides here. We'll finish the chapter. Okay, then we'll go on and get started in chapter 3. Okay, but we'll only and we'll go 2.5 hours, and then the last 2 hours will be the third lab for chapter 2. Okay, then that's next Tuesday. Next Thursday, we will continue in chapter 3 for 2 hours, then have the first lab for chapter 3, and that's a fun lab. It won't take you all that long, but we'll allow 2 hours for it, and then we'll have the test for chapter 2. So that'll be next Thursday. Sound okay?
Yes.
Okay. So, what I'm going to do is pause the recording. Understand with me moving around, this isn't going to pick up my voice always, but I'll try to do the best we can. Now we've got 3 groups of, okay. So, do we get? Oh, I need to call roll again. That's one thing I need to do. So let me do that. Because it looks like we're only missing one person now. I thought we were missing 2. Okay. Logan's still here. Jay's still here. Ethan is here. Amanda's here. Jonah's here. Patrick's here. Thomas is here. Latricia hasn't come in yet, right? Okay. So she missed the first part. Frank is here. Mendez is here. Mark is here. Where is Diamond? There you go. Okay. With the hood, I can't tell. Yeah, we're only missing 1. And Ryan's here. Okay. Did everyone get a copy of the lab? Okay. And I wound up with extra. That's what threw me off. I thought I had 13 copies made, and I have 2 extras. So.
Yes.
Did you get a copy of that? Oh, okay. That's what it is. Yeah, that's right. You were in the hall. That's right. Now it's making sense. Okay. 4, 4, and 4. Y'all split up very well. Okay. Now we're going to do projectile motion. Now this isn't how you would fire a projectile off a ship or a plane. Well, maybe a plane wouldn't be too far off from what we'll be doing. But what we'll be doing is projectile motion here, which is 2-dimensional motion. Okay? We're going to have horizontal motion and vertical motion. Now, to begin with, there'll be motion down an inclined plane, which is compound motion. It's both. But when it hits the table, it's going to be strictly horizontal motion. Okay? But then when it leaves the tabletop, it goes back to being 2-dimensional motion again. That's what we're going to be measuring. You're going to first measure the x component of velocity your velocity on the tabletop here. So that's why the meter stick's here, and you got the stopwatches somewhere close by. That's what you'll be measuring. Okay. Now, the vertical component will come when we're measuring the fall of the ball to the floor. We're going to have horizontal displacement and vertical displacement. Okay. Now, while the ball is on the track between the end when it hits the tabletop till it gets here, there's no net forces acting on the ball. That should be constant straight line motion. So that's what you're going to measure with your stopwatch when you're going to start the ball somewhere up the track. I'll tell you where in just a minute. And then you will let it roll down the track, but when it hits the table, that's when you start the stopwatch. When it rolls off the table, that's when you stop the stopwatch. So you're measuring that length where you have no external forces. Gravity's pulling down, but the table's pulling up. Your net force is 0. Okay? So that's what you're going to first measure. Okay? Then from there we'll go on. Okay? We will do, sorry. Can't talk. Okay? We'll proceed from there. And we got some sort of hefty formulas here, but I'm going to bring in the whiteboard and work on that and help you calculate some of the things they say here. So I'm going to go get that while y'all get started. So what you do first is, now, I want to make sure this hasn't been moved, okay? At some point, yours needs to move too. That's out, okay? Okay. I think all of you are okay there then. Okay, so the end of your track should be exactly 100 centimeters or 1 meter, right? Okay, pretty close anyway. So pick up your meter stick here with the 0 end down. You go on the ramp here, and where that's at 10 centimeters, I might need to move your paper, okay? Where that's 10 centimeters, that's going to be your starting point. Okay, and that's where you release the ball from. Somebody has someone has the stopwatch. And again, the stopwatch at 2 o'clock start, at 2 o'clock stop. That was 2.09 seconds to read this. Now, notice in your previous lab, some of you rounded to the nearest second. Don't do that. Do it to exactly what you read here, 2.09 seconds. Okay? Your 10 o'clock resets. Don't hit the middle button. Okay? Now, I'll get yours out. Oh, you already got it out of the thing. Okay? But what you're measuring, you're starting it when it hits the table here. You're ending it when it rolls off the table here. You'll hear it. So whoever's in charge of the stopwatch said. So on your on your data sheet on page 70, at 10 centimeters, that's where you're starting, 10 centimeters up the ramp, not up the ramp, 10 centimeters off the tabletop. Okay, you already got this measured. Stand it up. Yeah. And you're starting this where the ball is 10, starting at 10. Okay, yeah. And hit the ball. You see the ball? Yeah. Okay. You'll start it at 10 centimeters off the tabletop. Okay. And then somebody is going to somebody better have that in hand.
Oh, so we're not rolling it on it. I thought we was rolling it down the thing.
No. That was just to measure how far you were. Okay.
Our stopwatch looks like this, and we try to reset it.
What's that?
So if you hit reset, it doesn't do anything to it.
Okay, that's because you've not got any time on it. These LEDs are out. Their start, their stop. That's 1.31 seconds. That resets.
Okay, I thought it was a 7.
Yeah. No, it's just bad LED. Oh, look at that. Got it standing in place. Okay. All right. So you'll measure it 3 times, starting from the same 10 centimeters, okay? That's vertical 10 centimeters, okay? And you'll need to calculate your velocity. Okay, you start when it hits the table, stop when it falls off the table. Okay? How will you get your velocity then? Question, how will you get your velocity?
Distance,
What's that?
distance by time.
And what's your distance?
100 centimeters.
100 centimeters divided by the time. This time we're going to measure 3 different velocities. Now, if one of those times gets wacko from the other 2, redo that one, okay? But if they're all 3 fairly close, then calculate each velocity, then average velocities. We're not doing like we did last time where we threw out high and low times. We're averaging the 3 velocities, okay? And that's what you'll do next. The average velocity goes there, okay? So, while y'all are doing that, I'm going to go get the board because we're going to have some calculations to do later. I'm going to put this on pause order, okay? All right, the lab sheet said, I once upon a time had a lab sheet. Here it is. Lab sheet said on page 67, number 2, record and measure and record delta y, which you have done. And then it says solve delta y is equal to 1/2 g times delta x squared over v sub x squared for delta x. So the first thing y'all told me to do was multiply both sides of the equation by 2 v sub x squared. That got rid of the 2 in the denominator and the v sub x squared in the denominator on the right-hand side and moved it over with the delta y. Okay? So now we have our swap sides. The 2 went away on the right-hand side, now it's on the left-hand side. G times delta x squared is equal to 2 v sub x squared times delta y. Next thing we do, divide both sides by g. So isolate the delta x squared, divide by g. Okay? And that gave us delta x squared is equal to 2 v sub x squared delta y over g. But we don't want delta x squared, we want delta x, so we take the square root of both sides. That gives us delta x is equal to the square root of this whole quantity, 2 v sub x squared times delta y divided by g. But the problem with this, your v sub x was in centimeters per second, y was in centimeters, so we need the g in centimeters per second squared, not meters per second squared. And one of you told me 9.8 meters per second squared was the same as 980 centimeters per second squared, which is exactly right, and that's what we put in our formula. So y'all are calculating your delta x. Did you get an answer? Still working. Is it having trouble with the calculators or trouble with operating the calculators? You're okay? Okay.
Sorry, delta y is the
Delta y you measured.
Yeah, we
You
measured.
told me you wrote it down. Huh?
Oh, wow.
So,
Oh, okay.
yeah, because I wrote 199.
They're at 91.6.
How are you doing?
Pretty good.
You got a delta x yet? 48? Okay, is that in centimeters per second? Really? Delta x. That's a change of length. Okay, let's check the units. There was an issue with that. I'm just going to do the very thing we were doing only with units. Okay? That would be the square root of 2 has no units. That came from the 1/2. There's no units associated with that. V sub x was centimeters per second, but it's squared, so it's centimeters squared per second squared. The delta y was in centimeters, and then you're dividing by g, which is centimeters per second squared. Okay? Your per second squareds go out, these centimeters go out, and that leaves you the square root of a centimeter squared, which is a square root of centimeter squared. Square root of centimeter squared. Centimeter. The square root under the square. So this is in centimeters. Okay? Do you see that? Okay. So what kind of number did you get? 42 point something? 48.5 centimeters. You get one?
Yeah.
Whoa!
That's not bad.
Yeah, way too short. Let me see your numbers. Okay, you got 119.38. Did you square that? Oh, okay. What kind of number did y'all get? Get it yet?
I'm working.
Still working on it.
55.42908.
Okay, I think 55.4 will probably get it. Okay. What units will that be? Centimeters.
Is this better?
That sounds very good. Okay. Now, you've got your measures. Get your meter stick. Get it away from Thomas. He's playing with it like crazy. Get the meter stick from him. Okay. Now, where can you measure your horizontal distance from? Not there. Down here. It's going to be hard to measure from up here, but you can measure from down there. Now, allow a little bit for this. Allow for this. So it came off there. Okay. Okay. And mark off.
Yeah, that's him breaking down the formula of how you get.
Yeah. Your whatever you got. I believe that was good. Measure that in centimeters. Okay, but I sort of doubt this is going to fall in your seat there.
Yeah. He has it written up there too.
All right, that looks pretty. You have to line it up. Okay, not from anywhere, from your.
Yeah, I know, but I was just.
Yeah.
Yeah, it's going to come out about here.
Go back to 10. Right there, 10.
Oh,
Okay.
golly, bum, that's good. What is that?
Okay.
Right on the money.
Okay, wait. Have you measured?
Yes, I'm not
How?
with a pencil.
Yeah, but where did you mark it from? You marked
2 centimeters off of this.
Okay.
So it's 2 centimeters right there.
Okay. What did you use this?
Yes, sir.
Oh, you did. Okay, put the cup down there. We'll see if you're on. Okay. Now go from your 10 centimeter height.
Might need to move the cup a little bit.
There's your cup. I'll watch it. Just a meter stick. Whatever you measure, that's
Nope. Not a little short.
Didn't quite make it.
Okay. What was your measure?
55.4.
Yeah, that does seem a little long. You might want to check your calculations.
You drop it.
We had looks like they have 2 times 128.2, which is our average.
Wait, let me get the compact.
That might be one.
Alright,
You could do
maybe
that
all right.
probably in front of me.
Wow.
Okay. I was the computer.
Okay, how have y'all done? Oh, look at that! Right near it. Okay. How'd y'all do?
Yeah, it's all the
You kept moving out. Okay, I've seen y'all in lab before. Okay, I remember that first lab. Yeah. Okay. All right, good deal. You don't have to hit the cup. That was fun. Okay.
Yeah, we can do that. Yeah, you try.
Move it if you have to. No shake. 1, 2, 3. Hey, I got.
Oh! I hit the smack in the middle of it. Okay. Kept moving the cup. Okay, you can put it up. Okay. All right, then you can go to your 20 centimeters up, and and you don't use the cup anymore. So you put it, is that 20?
Yes, sir.
Up. Okay. Now, here's something.
4 points.
Right here.
Here's what I tried to do to begin with, is get these over as much against the edge as you can. Yeah, that's pretty promising.
We got something.
Good, are you ready? Yeah?
All right. Instead of 55.
It was 2.1.
Instead of 55.
Yeah, what it is, they want it, isn't what it is.
Yeah, y'all need to-
We're gonna do
Oh,
points.
yes.
By the way.
Yeah.
Yes, we have. We're still doing
Yeah, you start, there's a table there.
59.60. It's still off.
Okay. Go on. Oh, you've already started your next one, haven't you? Did you?
It's still here.
Okay, but wait, did you change your measure down here?
Yeah, we changed it.
It was down 2 centimeters.
2 centimeters. What was that from here to there? That's all right. I'll do the rest of your measure. You don't have to hit All right, that would have been nice. You're through with the cup. Yeah, that's all right. That's all right.
You already. Yeah, 30 is.
All right.
I don't think you can get it.
Calculations. In a minute, let's just go through. You finished page 67, or some of you have, repeating procedures for 20 and 30 centimeters, and you're working on your calculations. Is that right? Okay. So, on the results on page 68, make a graph with velocity on the horizontal axis and distance on the vertical axis. Okay?
So you want to do these 50?
Okay, yeah, I'm going to try to figure that out right now. Someone give me your range of velocities between the three, from the 10 to the 30. What's the range of your velocities? Right here, these.
119, 188.
Yeah. Okay, now, this one was way out of line here. You average these together, you have that? You added them together, got that. Divide by 3.
Is 2 not done right? 2 is not done right. What's 30?
Okay, what's your range? 111 to 190, let's say. Okay, and then what's the other one you jumped in?
I forgot to
81.
multiply.
Okay. So, give me a,
The average velocity is at 155.4.
so let's do your velocities. Turn your graph so it's landscape mode, like this. Okay? Let's say 100 is here, 100, and 10, 20, 30, 40, 50, 60, 70, 80. Does that cover everything you got?
Yeah, that hits it over.
Okay, so what now?
That probably messed up your other calculation as you drive the thing back.
Oh, yeah, I fixed it.
Oh, you did.
We didn't ask for anything else. So,
Okay, they got the 190, that was everything, right? Okay, your other was 40 to 48. Okay, so you need 40, 50, 60, 70, 89. So why don't you do 30, 40, 50, 60, 70, 89?
I'm blaming you on the graph.
no clue.
Yes.
We don't know what to do on our graph.
Okay. Let's see what your numbers look like. Okay. Your V sub x is about 120 to 190 approximately. Okay? So why don't you do, let's try this, 110, 20, 30, 40, 50, 60, 70, 80, 90. That works. Okay? And then when you get that, we'll work on the vertical.
Wait, so the last one is 100?
How are y'all doing?
The second one, I know you should everybody else, the 17 shop was down last time, so the second.
That sounds good. Okay. Oh,
He gonna write it down. I'm gonna write it down. This man right here gonna be like, he got slurred, the boss will be good.
No, 100 good.
Let him do it. You do it.
Okay, yeah, what do we shoot? 100, 110, 20. Yeah, you go about 10, so. This is one you Oh, and everything, somebody put out that was one you did. Okay. By the way, y'all have some rulers down here and one over there. So when it gets time to do the graph, that's what you use.
I guess.
Thank you.
Yes, he That's what he can do, the type, didn't he?
The vertical is distance. It's always 90.
88.3.
Wait, or is distance? What is distance? How far away? What is distance? Is distance this?
Yeah, you're delta X.
Okay, distance.
So it's the box.
And it goes from,
What's our highest delta?
so let's do it this way. This will be, I think what I'm shooting for, to 30, 40, 50, 60, 70, 80, 90. That sort of centers it. Yeah, 30 at the bottom.
Vertical distance.
That's a George.
Yeah, someone got to do that.
Okay. So everybody's finished with the board now, is that right? Okay. I'm going. Okay, after every team had calculated their average VSUB X and their delta X for all three distances above the tabletop, 10, 20, and 30 centimeters above the tabletop, now they're plotting on their graph paper on the horizontal scale in landscape mode. Horizontal scale would be your VSUB X, and that was approximately going from 100, 110, 20, 30, 40, 50, 60, 70, 80, up to 190. And on the vertical scale, that's the delta X, going from 30, 40, 50, 60, 70, 80, 90, 100. So that's what they're plotting their data points now.